Hello and welcome to ATI 4640. In the last session, we addressed the different costs of inventory and the main objective, which was to minimize the total inventory cost. We mentioned the different independent demand models, the basic economic order quantity, the production order quantity, the quantity discount model. And we started with the basic economic order quantity. Uh, in this session, we will continue addressing the other two models and define the reorder point. The economic order quantity model answers the how much to order quantity or question. So basically we are asking with that model, with what we did with the other model, we just asked how much do I need? How many units do I need to order? A simple inventory model will assume that the receipt of an order is instantaneous. So basically when an order, I will receive my order, which means the firm will place an order when the inventory level for an item is zero. When it's zero, I will order. When I don't have it, I will order. And I will receive it immediately. I'm assuming that I will receive that immediately. But in fact, there will be a time between placing an order and receiving that order, which is called lead time. Considering that the lead time might be days, weeks, or even months, the firm should not wait until they have zero inventory of an item to order. The firm should identify the reorder point, which tells the firm when the order considering lead time. The reorder point will equal demand per day multiplied by the lead time for a new order in days. The demand per day can be found from dividing the annual demand by the number of working days in a year. Graphing the relation between inventory level in units and the time, we can identify the slope as daily demand. So the daily demand is the slope for that line, and we can identify also the optimum order quantity, which is Q star or Q optimum or Q asterisk, and the reorder point considering lead time. The example in this slide is for an Apple store that has a demand of 8,000 iPhones per year. With 2 weeks vacation, we have 250 days as considered as working days. So the lead time for orders is 3 to 4 weeks or 3 to 4 working days until you receive the items that you ordered. So we need to calculate the reorder point. First, we need to find the daily demand, which will equal the annual demand divided by the number of working days. The daily demand will equal 8,000 divided by 250 days, and that is 32 units per day. The reorder point will equal the daily demand multiplied by the lead time, which will equal 32 times 3 if it's 3 weeks, and that's 96 units, or 32 times 4, and that will be 128 units. So either when we have 96 in stock, I will order, or when I have 128 unit in stock, I will start reordering. And again, the reorder point or the Q star, or what we need to order is 96 units or 128. When we have 128 in stock, they should order the Q star to replenish their inventory. The second independent demand model is the production order quantity model. Because this model is suitable for production environment, it's commonly called the production order quantity model, which can be applied in two situations: when inventory builds up over a period of time after an order is placed, and when units are produced and sold simultaneously. So using the following symbols, we can determine the expression for the annual inventory holding cost for the production order quantity model. Now remember that all what we care about is the holding cost, minimizing the all over cost, and that's by minimizing the holding cost and the setup cost. So we need to find both the holding cost and setup cost. So let's use Q as the number of units per order, P as the daily production rate, and H as the holding cost per unit per year. D, lowercase d is the daily demand usage rate, and T is the length of the production run in days. So the annual inventory holding cost will equal the average inventory level multiplied by holding cost per unit per year. But the average inventory level will equal maximum inventory level divided by 2, and we saw that in the graph. And the maximum inventory level will equal total produced during the production run minus total used during the production run, that is PT minus DT. Based on the maximum inventory and the annual holding cost formula, the holding cost will equal PT minus DT divided by 2, all multiplied by the holding cost per unit per year. Assuming that the total produced is the number of units per order, Q, then Q will equal daily production rate multiplied by the length of the production run in days, which means that the length of the production run will equal to Q divided by P. So substituting T with Q divided by P in the annual holding cost formula, it will be annual holding cost equals Q over 2 multiplied by 1 minus D divided by P multiplied by H. Or in other words, half QH multiplied by 1 minus D over P. Half QH multiplied by 1 minus D over P. And that's our formula. So if the setup cost is the annual demand divided by the number of units per order multiplied by the setup cost for each order, and the holding cost is equal to half QH multiplied by 1 minus D over P, we equate both formulas as we did before in the previous model. So we can find that point or the number that we need to order when the reorder comes, or the time to reorder comes. So we equal D over Q times S equal to half HQ multiplied by 1 minus D over P, with a little algebra and moving stuff around. We can find that the optimal production order quantity Q star will equal to the square root of 2ds divided by H multiplied by 1 minus D over P. A manufacturing company forecasted demand for the next year to be 1,000 units. With an average daily demand of 4 units per day, the production process is most efficient at 8 units per day, but uses 4 of them per day. So production is 8, uses 4. The company would like to solve the optimum number of units per order, knowing that setup cost is $10 per order, the holding cost is 50 cents per unit per year, and the number of working days per year is 250 days. We can find the optimum number of units using the formula. So we have the Q star for the production is equal to the square root of 2ds divided by H multiplied by 1 minus D over P. Uh, we have the demand as 1000 unit. That's the annual demand. So the uppercase D is the annual demand, the lowercase is the daily demand. And S is equal to 10. H, the holding cost, is 50 cents per unit per year. And the lowercase d is 4 divided by P, which is 8. So, substituting all that, we will get the square root of 80,000, which will equal 282.8 hubcaps or wheels. When using annual data, the equation becomes the Q star will equal the square root of 2ds divided by H minus H multiplied by 1 minus the annual demand rate divided by the annual production rate. The third independent inventory model is the quantity discount model. Most companies either offer or receive quantity discounts for at least some products. The quantity discount is simply a reduced price for an item when it's purchased in large quantities, and we see that all the time. You know, when you buy in thousands is different when you buy in one or two items, and you see it on some sites for discounts when you buy large amounts. An example of quantity discount schedule is shown in the table, and if you purchase from that table, you can see that if you purchase from 0 to 119, the price per unit will be 100, but if you purchase 120 to 14.99, the price per unit will be 98, and if you purchase 1500 and up, then the price per unit will drop down to $96. And again, although the drop is not that much, like $4, but if you multiply the $4 times the 1000 or 2000, either 1500 or 2000 units, it's a huge amount of savings. The total annual cost in this model will equal setup cost plus holding cost plus product cost. So TQ or TC will equal to D divided by Q S multiplied by S plus Q divided by 2 multiplied by IP plus PD. Where Q is the quantity ordered, D is the annual demand in units, S is the ordering or setup cost per order, P is the price. This is uppercase P, which is different than the lowercase p. This is the price per unit, and I here is the holding cost per unit per year expressed as a percentage of the price P. So this is a percentage, it's not like the H, which is the holding cost per unit per year in dollars. So this is a percentage. And the Q star at this point will equal to the square root of 2ds divided by IP. Because unit price varies, holding cost is expressed as a percentage, and that's why you you can use it here as a percentage and not as a dollar amount. There are two steps in analyzing a quantity discount. Starting with the lowest possible purchase price, calculate Q star until the first feasible economic model or economic order quantity is found. This is a possible best order quantity along with all price break quantities for all lower prices. and then we calculate the total annual cost for each possible order quantity determined in step 1. Then select the quantity that gives the lowest total cost. And this is the, again, the idea of this is to get the lowest total cost, or minimize the total cost. The graph in this slide shows the annual total cost versus order quantity, showing the three options with no discount, discount number 1 and discount number 2. The lowest with discount number 2 at $96 will be at 278, but the quantity discount for the that one will not start until the order amount equal or exceed 1500. So 278, which is here, will not be feasible because this one is not meeting the criteria. I will not give you this discount. The company will not give us that discount until you purchase 1500 and up, 1500 and up. So whatever you purchase below 1500 will not be feasible, or will not apply to it the discount number 2, the $96. So what will be the other solution? So the next lowest will be the 275, and that is with discount number 1, 275, and with 275 it's $98 per unit, but it's cheaper than if I want to order 1500. So for me, this one is not feasible. This one is not feasible. This one is feasible and will give me the lowest when I buy 275 items. So this will be the first option, and then the next option, once I start ordering 1500 and up, then I will start qualifying for discount number 2. This slide confirms the graph showing that the 278 with discount 2 option is not feasible, and the next option will be the 275 but using discount number 1 at $98. The 275 will be optimum quantity for the quantity discount model that with a total annual cost of 51,000 excuse me, it's 517,155. So for what we discussed was the most popular form of a single purchase quantity discount called the all units discount. In practice, quantity discounts appear in a variety of forms. For example, incremental quantity discounts apply only to those units purchased beyond the price break quantity rather than to all units. Fixed fees such as the fixed shipping and processing costs for a catalog order, and we have item aggregate pricing function that allows users to set up sale items that can be grouped together for the purpose of calculating quantities to meet price breaks. Other discounts might be in the form of truckload discounts, buy one get one free offers, and one-time only sales. All the inventory models that we have been discussing so far or in previous slides and the previous session made the assumption that demand is constant and certain. The probabilistic model are used when product demand is not known but can be specified by means of probability distribution. Probabilistic models are real world adjustments because demand and lead time won't always be known and constant. And an important concern of operation managers is to maintain an adequate service level in the face of uncertain demand. One method of reducing stockout is to hold extra units in inventory which is referred to as safety stock. Then the reorder point will equal daily demand multiplied by order lead time, and we add to that a safety stock to achieve the desired service level. The annual stockout cost will equal the sum of unit shorts for each demand level multiplied by the probability of that demand level multiplied by the stockout cost per unit multiplied by the number of orders per year. So basically we can calculate if you don't have enough stock, or you are done with stock in your store, and people are coming to buy and did not find the item, that will cost you certain amount, and we call it the annual stockout cost. When you don't have in stock what people need, then at that point actually there is a cost for that, and we can calculate it using this formula. In this example, if the reorder point for eyeglass frames is 50 units, the carrying cost per frame per year is $5. Stockout cost due to the lost sale is $40 per frame. The store was experienced the probability distributions shown in the table. If the optimum number of orders per year is 6, how much safety stock should the optical company keep in hand? And you can see that the probability of 30 units sale is 20%, 40 20%, 50 is the 30%, 60 is 20%, and 70 is 1%, and that's a total of 100%. So with the zero safety stock, if the demand was 70 and with 50 units in stock, only I have 50 units in stock, then the shortage will be 20. The probability for that to happen is 10%. The stockout cost per frame is $40. With 6 orders, the cost will be $480 for those units, and there is a 20% chance that the demand will be 60, and at that point we are short 10 units. So it's, the out of stock is 10, with also the cost of 480. If you calculate that, it will be 480, because we can multiply the 10 multiplied by the 20% of a chance of probability for 60 demand to happen, and $40 stock out cost, and 6 orders per year, then we have 480. So 480 plus 480 for the 70 probability of having 70 in demand, then we have $960. That will be the total cost if I have zero safety stock. So it's costing us total cost of $960. Now if we have 10, with 10 the total cost will be 240. So with 240 and I have a holding cost of 50, the total cost will be 290. With 20 safety stock frames, it gives the lowest total cost of 100. Why? Because the stock out cost is 0. I don't have a problem with having stock out, because I have 20 safety stock that will actually help me in any demand during that period of time. But I will have additional holding cost, and the holding cost will be 20 times $5, and that will be $100, and that will be the total cost only. So when it's difficult to determine the cost of being out of stock, the operations manager may decide to follow a policy of keeping enough safety stock on hand to meet certain customer service level. again, you can do that by calculations, or with experience, the operations manager over time, they will know exactly how much safety stock they need to have in inventory, so they can manage or they can fulfill the demand. Assuming that demand during lead time follows normal distribution, only the mean and standard deviation are needed to define the inventory requirements for any given service level. So if the expected number of kits needed during lead time is 350, as shown in the graph, for 95% service level, we can add safety stock of 16.5. Based on that, the reorder point will be 366.5. With the normalized distribution and knowing the standard deviation of demand during lead time, and when the cost of stockout cannot be determined, we can use prescribed service levels to set safety stock. Based on that, the reorder point can be calculated by adding the Z sigma to demand during lead time. Z is the number of standard deviations, and the S DLT is the standard deviation of the demand during lead time. The probability of no stockout for 95% of the time, we have the risk of stockout 5% at that point of the area of the normal curve. And if the mean demand is 350, then we can find the number of standard deviations required to make sure that we have the safety stock to service with 95% service level. And that's how we got that 16.5, and we added that to the 350. So if mu is equal to the average demand, which is 350 per kits, sigma DLT is equal to the standard deviation of demand during lead time, which is 10 kits. The stockout policy is 5%, service level of 95%. Using Appendix I, we have like table that will show us the Z value for 95%, which will equal to 1.645. So the safety stock is equal to Z multiplied by sigma. That's 1.645 multiplied by 10, or 16.5 kits, and the reorder point will be 366.5. Since I'm dealing with kits, not there is no halves, then I can round it up to 367 kits. When data on demand during lead time are not available, there are other models available. When demand is variable and lead time is constant, when lead time is variable and demand is constant, when both demand and lead time are variables. Demand is variable and lead time is constant, then the reorder point will equal to the average daily demand multiplied by the lead time in days plus the Z sigma DLT. Where again the standard deviation or sigma DLT is equal to sigma square root of lead time, and the sigma D is the standard deviation of demand per day. For example, if we have an average daily demand normally distributed equal to 15, then lead time in days constant will equal to 2, and standard deviation of daily demand of 5. The service level will equal to 90%. The reorder point will equal to 15 units multiplied by 2 days plus ZS DLT. Z for 90% of service is equal to 1.28. That's from the appendix, from the table that we have at the appendix, and will give us the Z value for each level of percentage of service. Substituting the values, we will find that 30 plus 1.8 1.28 multiplied by 5, the square root of 2, and that will equal to 39.02, or we round it down to 39. So safety stock is about 9 computers. So if I have 30, then I have to add 9 as safety stock. The lead time is variable and demand is constant. The reorder point at that point will be daily demand multiplied by the average lead time in days plus z multiplied by the daily demand multiplied by the sigma LT, where sigma LT is the standard deviation of lead time in days. For example, if the daily demand constant and equal to 10, average lead time is 6 days, standard deviation of lead time equal to S, which is equal to 1. The service level equal to 98%, so Z from appendix I is equal to 2.055. Replacing or substituting the values with the reorder point formula, we will get 80.55, or round it up to 81 cameras in this situation. If both demand and lead time are variable, then the reorder point will equal to the average daily demand multiplied by the average lead time plus Z multiplied by sigma DLT. And again, remember that sigma D is standard deviation of demand per day, sigma LT is the standard deviation of lead time in days, and sigma DLT is the square root of average lead time multiplied by sigma D squared plus the average daily demand squared multiplied by sigma squared LT, or sigma LT squared. For example, if the average daily demand normally distributed with 150, standard deviation SD or sigma D is equal to 16. Average lead time 5 days, normally distributed, standard deviation sigma LT is equal to 1 day. The service level of 95%, so Z is equal to 1.645. The reorder point will equal to 150 packs multiplied by 5 days plus 1.645 multiplied by sigma DLT. But sigma DLT can be calculated from the square root of the 23,780, which is almost 154. Substituting in the formula above, the reorder point will equal to 1003 packs. The single period model is a system used for ordering items that have little or no value at the end of the sales period, like perishable items. Cost of the shortage, CS, is equal to sales price per unit minus cost per unit. The cost of average, the cost of overage is equal to cost per unit minus salvage value. The probability of not stocking out or service level is set to cost of shortage divided by cost of shortage plus cost of overage. So if the average demand is equal to 120, which is mu, equal to 120 papers per day, and the standard deviation sigma is equal to 15 papers, the CS cost of shortage is equal to $1.25 minus 70 cents, which equal to 55 cents, and the cost of overage is equal to 70 cents minus 30 cents, which is 40 cents. Then the service level will equal cost of shortage divided by cost of shortage plus cost of overage, which will equal to 0.55 divided by 0.55 plus 0.40, and that will equal to 0.579, or 57.9% level of service. From appendix I, for the area of 0.579, Z will equal to 0.1 199, the optimal stocking level will equal to 120 copies plus the 1 point or 0.199 multiplied by sigma, which will equal 120 plus 0.199 multiplied by 15, and that is equal to 123 papers. So the stock out risk is 1 minus the service level, which is 1 minus 0.579, and that will be 42.1%. The risk of or the probability of being stuck out will be 42.1%. The inventory models that were introduced are fixed quantity, that is the same fixed amount is added to inventory every time an order for an item is placed. The reorder point will be event triggered. This requires a continuous monitoring of subtraction or subtracting and adding items to trigger the event reordering. In the fixed period system, which also called a periodic review or a P system, inventory is ordered at the end of a given period. Then and only then inventory on hand will be counted. Only in the amount necessary to bring total inventory up to the target level will be ordered at that point. Fixed period systems have several of the same assumptions as the basic economic order quantity in the fixed quantity system. Only relevant costs are ordering and holding. Lead times are known and constant. Items are independent of one another. If those assumptions were not to be satisfied, then if any one of these assumptions is wrong or not satisfied, then we cannot apply this fixed period system. Various amounts are ordered at regular time instances based on the quantity necessary to bring inventory up to the target quantity. So with this, the fixed period, then we are looking at every 3 months or every quarter, we are going to order quantity. Now the quantity will depend on what do I have in the store and what will be the demand, and that's why we have different quantity orders. So sometimes I'll order Q1, sometimes I'll order Q2, and sometimes I have to order Q3, and as you can see, Q3 is the largest amount here. So it depends on the demand at that period of time or that quarter. So what we did at certain times or certain period of time, every 3 months I will order a certain amount, and it's not based on a fixed number of units being ordered. It's based on fixed period of time. In fixed period system, inventory is only counted at each review period, may be scheduled at convenient times, appropriate in routine situations, may result in stockouts between periods, may require increased safety stock. So with this, talking about inventory and inventory model, that will be all for inventory management and inventory models. And as I stated before, all the models introduced in this chapter are independent models. Dependent models will be covered in another chapter. If we can get to that chapter, then we will do it at that point. Thank you and have a great day. If you have any questions, just let me know. Have a great day.